Thanks for agreeing to review this proposal. This video is intended to help you get a quick summary of the ideas behind this proposal. So, sparse recovery, we focus on three problems as examples. Compressive sensing is when you have a vector x, the real vector, it's sparse, so only k of the components are non-zero or approximately k are non-zero. And the goal is to reconstruct x from y equals ax from linear measurements. And as you possibly know, there's a lot of work that's been done on taking relatively few measurements, k-log n measurements, to reconstruct x reasonably well. Group testing is sort of like a non-linear version of compressive sensing. In this case, the measurements that you take are binary. The input itself, the x vector itself, is binary, and the measurements are non-linear because you get a 1 if even one of the items in the pool is a 1, otherwise you get a 0. Network tomography is a version of compressive sensing or group testing where uh, the the measurement process is heavily constrained. So you're given a network and you have to carry out measurements based on the network. For example, end-to-end measurements and trying to figure out the end-to-end path delay. The PI has worked in each of these different fields, and this proposal attempts to combine the insights gleaned from each of them. The challenges in this are threefold. We have to minimize the number of measurements, we have to use low decoding complexity, and the algorithm should be robust to noise. The essential ideas that we use are essentially that in each of these there's some structure to the data, so we can hope to compress it. We can try to get more from less. We also want to get algorithms that are very quick. So the essential idea here is that our compression had better be designed in a manner such that they can run very quickly. They can decode very quickly. So every step you should get something non-trivial. And to get robustness from noise, we use ideas that are not too uncommon in coding theory and information theory. But the challenge is to design codes that are robust to noise without sacrificing the speed. One work that the PI has done that he's really proud of is on compressive sensing. It's on order optimal compressive sensing. So this figure over here represents the decoding complexity along the x-axis and the number of measurements along the y-axis. And much of the prior work focused on taking order k log n measurements and trying to reconstruct y and LP. So that would be somewhere over here. Our work was essentially the first, which was order optimal. It took order k measurements and had order k number of operations of decoding complexity. So and in fact, it turned out to be order optimal even information theoretically in the number of bits and various other nice properties. So the essential algorithm over here is iterative. It's based on the figures figures 4 and 5 at the end of this, and we'll talk about that at the end. But one of the basic ideas that we use in this proposal is based on this algorithm. Another idea that we use quite a lot is the LP formulation for group testing. So as you recall, the group testing problem is a non-linear version of compressive sensing. So it's not clear that using LP decoding algorithms, which are common in compressive sensing, would work for group testing. Again, the PI and his collaborators were some of the first people to look at the linear programming version of this. And the essential idea here is that you take the non-linear program, you linearize it. So the x's are the vectors, are the variables you want to reconstruct. Y's are the measurements, and you introduce noise parameters in case you have noisy measurements. You can linearize it, you can relax the linear program, and it turns out by some careful perturbation analysis that this all works. Let's talk a little bit about the ideas used in the quick decoding algorithm. So, so the essential idea there is that we want to use a very sparse but structured sensing matrix. So if the if the input vector is sparse, the output vector is a linear combination of the input vector. We want to choose a sensing matrix that is sparse to begin with, sparse and structured. So what does that mean? it turns out that one can choose a matrix which is sparse, which has constant degree on the left. That is, every input is measured only a constant number of times, such that at the output there will be many so-called leaf nodes. That is, there'll be many measurements at the output which will depend only on a single input variable. Of course, the decoder doesn't know a priori which variable it is that depends only on a single input, but via iterative peeling processes that are used, for example, in LDPC decoding and so on, one can successively and iteratively cancel these out and get essentially order optimal performance. So again, order k measurements, order k time, one can do this. The algorithm itself proceeds by uh, proceeds in an iterative manner. It it examines nodes on the right, checks to see if they satisfy certain properties. If so, then it estimates some non-zero value on the left, and then goes back, updates the measurement vector, and does it again. Every step over here takes constant time. So to reconstruct a k-sparse vector takes time, which is order k. uh, we have we have simulations, and our simulations show that in fact these are extremely efficient. So the as the length of the signal increases, the number of measurements required do not change. As the number of measurements increase, as the sparsity level increases, the number of measurements required scales linearly in the sparsity instead of as k log n. All right, let's talk about. So this is prior work. Let's talk about what we propose to do in this proposal. So we propose to focus on three particular problems: compressive sensing, group testing, and network tomography. In each of these, we have ideas that we want to build upon prior work to do something. In compressive sensing, one particular idea is the application of our extremely fast algorithm is very promising. Consider a setting where there's a single transmitter, multiple receivers. So these receivers are cell phone users. So they all want to communicate with the base station. Now, in general, if you want to do interference-free transmission, then you have to carefully schedule, or you have to use some careful uh, scheduling schemes. So, for example, Aloha is one way of doing it. But with that setting, interference is allowed, and in fact, it's desirable. It turns out that uh, that a natural that one can design scheduling algorithms where a certain amount of limited interference can be encouraged, and then with successive cancellation decoding, one can hope to achieve good performance. So one of the directions we want to go forward is to take our extremely efficient algorithm and to make it and to showcase the fact that it helps significantly in terms of throughput and ease of scheduling for wireless communication problems. Um, the problems and challenges in this direction are our analysis so far has been extremely idealized in the sense that we've assumed that any noise is Gaussian, that that the that the process itself is that the input noise that the noise at the source is Gaussian, that the noise at the destination is Gaussian. So we need to be able to handle different noise models. We also need to be able to handle different statistics. For example, in the wireless problem we just talked about, we can't really control the measurement process. So we'd better make sure that our analysis also works for general measurement processes. We have ideas on how to do these things via standard techniques in probability theory, but the challenge is to merge very fast algorithms, robust to noise, with very few measurements, with the standard uh, techniques from probability theory. For details, we encourage you to look at our write-up. It's available on archive, and we're working on it. For group testing, as we noted, group testing is a nonlinear version of compressive sensing. So order optimal algorithms already exist in terms of the number of measurements, but very fast algorithms are relatively few. A couple of people have looked at very fast group testing algorithms, but they're not order optimal. So, so the challenge over here is that since the measurements are non-linear, so successive cancellation doesn't really work. So one potential idea that we have is to use coupon collection as a measurement process. So if we just take a sufficient number of measurements, it turns out a rough calculation indicates that if we take d log n measurements, then we can end up with a very efficient algorithm. So in the adaptive setting, we can actually achieve order optimal performance in both the measurement complexity and the decoding complexity, order d log n. Even for the non-adaptive setting, if we take um, uh, if we use the coupon collection problem, and we have to use some other ideas, because again we have to decode very efficiently. So in very small number of iterations, we need to be able to estimate one non-zero input at the source. So we have to combine ideas from coding theory. In particular, we're examining the use of expander codes and seeing what happens. Simultaneously, we're also looking at our LP decoding algorithm. If you recall, we talked about the fact that we also have LP decoding algorithms for group testing. So the idea over here is that in this case, we might, because it's a very special type of LP, the inputs are binary, the measurement vectors are binary, the noise itself is binary, we should therefore be able to uh, speed up the generic LP decoders and come up with faster solutions. So again, we have some ideas over here as to how to modify existing LP decoding algorithms to work faster for this LP. Um, Lower bounds that exist for the group testing problem are decent, but they're not optimal. So most of the lower bounds are essentially off by a constant factor. And these lower bounds are very loose, it turns out, for problems like threshold group testing, where you could have a 0 if there are fewer than a certain number of items in a test, or a 1 if there is more than a certain number of items in a test, and in between it's random. So for example, if you're testing someone's blood, and if there are very few germs in it, then you'll get a 0. If there's too many germs in it, then you'll get a 1. And in between, it will be sort of random. In this model, it's known that you need more tests, but how many more, we don't really know. So we have some ideas over here based on computing the sums of certain classes of random variables. And it's a tricky combinatorial problem, but we have preliminary results which seem to give non-trivial lower bounds for this problem. Again, this is work under progress. We're trying to see how good this is. Um, Finally, we want to expand the work in this direction and look at more general and more realistic models of group testing, such as semi-quantitative group testing, which allows for multiple levels. So if the number of germs in a sample is too few, you'll get a 0. If it's above a certain threshold, you'll get maybe something like a 1. If it's above even a further threshold, maybe a 2, and so on. So, because in general, things are never quite linear nor non-linear. That's somewhere in the middle. They're approximately linear, perhaps. So, how does one handle something like this? Again, our lower bound techniques and our LP decoding techniques show promise. We're analyzing. We're in the process of analyzing what happens here. Finally, in the case of network tomography, we notice that the techniques that we mentioned already don't necessarily work. Both of the prior regimes require uh, fairly structured types of matrices with some guarantees on the randomness over there. Um, but in the network tomography problem, one can really only sample uh, from from distributions that are induced by the network itself. One can only take end-to-end measurements in the network tomography problem. So in this setting, we want to do things like estimate which parts of the network are congested, or which parts of the network has changed recently. So in this setting, one idea that we have is to look at uh, random walks on networks. So imagine that we send packets on random walks through the network. And in this setting, then we would be able to simulate something like a random sampling process that we've been using for compressive sensing or group testing. Um, so again, preliminary analysis already seems to indicate that we are significantly faster than existing tomography algorithms. However, this random walk does introduce a factor that corresponds to the mixing time of the graph. Again, this mixing time is already there in other previous algorithms, but it could be potentially large. So the mixing time of a walk on a straight edge network, for example, is order n, whereas if we did something naive, we would be able to build something better than this. So, our approach in this direction is to actually analyze the structure of the graph, and try to see what we can say about network tomography problems via our ideas in compressive sensing, and also to see if in the group testing version whether we can use the ideas that we had from the group testing algorithms, the LPD coding, to say anything about this. Um, Lastly, we so these three particular problems we have some concrete ideas in, and that's why we have so far we've discussed particular concrete approaches that we could take to handle these things. But in fact, we believe that in fact our techniques, our algorithms, the iterative algorithms and the LP-based algorithms, and also the analytical techniques for these algorithms and the analytical techniques to prove lower bounds for these for any algorithm for these problems are in fact fairly general. So we've already mentioned threshold group testing, network tomography, semi-quantitative group testing, but we believe that even for things like matrix recovery problems, quantized compressive sensing, or sparse sampling problems. Um, these are all also examples of sparse recovery problems. We believe that our techniques should have some power. So to summarize, we're very excited about our techniques, about our existing results, and our ongoing work is extremely promising. We hope to make significant progress in this. Thanks for listening.